All right, everybody. Oh boy, I love spectral graph theory so much. This is going to be great. I will recap some things I talked about in the last lecture. So in spectral graph theory, we're going to be talking about undirected graphs, G. And that'll be like fixed at the beginning for all time. The graph we're considering. Self-loop's OK. Parallel edge is OK. And what we'll really be focusing on is functions. Functions labeling the vertices of the graph by real numbers. And if there are n vertices, then the set of all such functions mapping the vertices to real numbers forms an n-dimensional vector space. You can just stack all the function values into a column vector, and that's your vector space there. And I should also mention, we had a whole lecture on analysis of Boolean functions. And analysis of Boolean functions is really just this whole theory restricted to the special case where G is the hypercube graph, this one right here. So there, of course, we're also thinking about functions mapping, Boolean strings to real numbers. And it's just the special case of all this theory where this is our graph G. So now we'll study it in general. I should also add that if this is the first, few times you've seen this stuff, definitely just imagine in your head that the graph is a regular graph, because that makes a lot of things simpler. One thing in particular it makes simpler is this. I mean, this is the weirdest thing that it takes a little getting used to. So we're going to be talking about this vector space of functions mapping vertices of the graph to real numbers. And we're going to have an inner product in this vector space, but it won't be the usual inner product. It'll be a different inner product, which is allowed by the laws of linear algebra. And we'll write it like this with angle brackets, subscript pi. I'm going to stop writing the pi everywhere, though, because this will be the only inner product we use. So the inner product between two functions is sort of the correlation between them. But when you draw the vertex u from a certain probability distribution, a very special probability distribution on the vertices, which I'll denote as pi. And this special probability distribution will just be the uniform distribution in the case of a regular graph, which is why it's easiest to think about regular graphs. But in case you have an irregular graph, then you have a different probability distribution to care about. So this probability distribution pi, which is called the invariant distribution or the stationary distribution, there's two ways to define it. One way to define it is just by sort of giving a little algorithm that draws from pi. And that little algorithm is draw a uniformly random edge, uv, but then output, let's say, the first vertex u. It's actually the same as if you decide to output the v, because if you draw a uniformly random edge from u to v, you're equally likely to pick the one going from v to u. So as I mentioned in the last lecture, we're only going to be thinking about undirected graphs, but sometimes we'll really think about that undirected edge as like a directed edge from u to v and a directed edge from v to u. Okay, so this probability distribution is more likely to pick vertices with higher degree. And indeed, it's not hard to check that you can just write down a formula for this special distribution. The probability mass that put on a vertex u under pi is proportional to the degree. It's exactly the degree divided by, well, the number of directed edges, 2 times m, the number of undirected edges. Okay, so this is just like it's like similar to like the usual dot product between two vectors. You line up all the f of u values and the g of u values, you multiply it together and add them up, but you add them up with some weights where the weights are proportional to the degree. Okay, so this will make things go more smoothly. All right, so why is it called the invariant distribution or the stationary distribution? It's to do with what's written on this half of the board. So one thing we're really going to ultimately care about, and we'll talk about somewhat in this lecture, is the following. Let's say you do the standard random walk, that's what this stands for, on the graph. That means you're at some vertex, and at each time step, you choose a random neighbor of it and walk to that neighbor. Now, what we'll eventually be concerned about is like what happens, if you're concerned about where you'll end up after a while if you start from an arbitrary or worst case starting point u0. But if you start from the probability distribution pi, then you'll always stay in that distribution. So what do I mean by this? It took me a while when I was first learning this to get my head around it. When you're doing a random walk in a graph, your first instinct is that, okay, at each step you're remembering like what vertex you're on. But you should also think more generally of doing a random walk and thinking of at each time step, what is the probability distribution of vertices you might be on. So once you fix a starting vertex, u0, and you walk for 10 steps, at each time step, in particular the 10th step, you have a probability of being at each vertex. And you should really imagine how this probability distribution on the vertices evolves over time. And you can even imagine not starting at some worst case vertex u0, but picking your starting vertex from a probability distribution on vertices as well. And a magical thing happens if you pick it with this according to this probability distribution pi. Then, of course, your 0th vertex is in this probability distribution pi. But also, as we saw in the last lecture, now the first vertex will also be in probability distribution pi. And the second vertex will also be in probability distribution pi, and so forth, no matter how many steps you take. And that's why it's called the invariant distribution. Once you're in this probability distribution, you will continue in that probability distribution forever when you do a standard random walk. Okay, and again, this is just the uniform distribution on all vertices in the case of a regular graph. Otherwise, it's proportional to the degrees. And a major thing that we're eventually going to study, we talked about before, is, well, if you start from a worst case vertex, how many steps do you need to take before you're sort of close to being in this distribution? Great. So now once this inner product is chosen, and we have a vector space, we can start doing some linear algebra, which is where the spectral graph theory kind of gets its name. And really, much like with analysis of Boolean functions, the special case where the graph is the hypercube graph, in some sense, what we really care about is functions from the vertices to 0 and 1. Okay, we care about Boolean valued functions. We care about subsets of vertices. These are the things that usually interest us. We extend to the case of real valued functions because, it's mathematically natural and it helps us study the Boolean valued case, ultimately, that we care about. But we're always going to be coming back to this case in where you're looking at 0, 1 functions or indicators of subsets of vertices. Okay, that's what I've written here. If f is the indicator of a subset S of vertices, well, then many of these linear algebra things that we'll be mentioning have a nice meaning. So for example, last time we introduced this notation, the squared norm of a vector or function f. In this setting, we use the words vector and function interchangeably. This is the inner product of f with itself. And by definition, this is the expected value of, or the average value of f of u squared, the average squared value of the labels, as always under this probability distribution. When f is 0, 1 valued, though, finally, f of u squared is the same as f of u. 0 and 1 squared are themselves. So now you have the expectation of just f, which is expectation of an indicator. It's the probability of the event being indicated. So in the end, it's this quantity. It's the probability that a random vertex is in the set S, which in the regular case, when pi is the uniform distribution, is just the fraction of vertices that are in S. And sometimes it's called the volume of S. It's a fractional volume. So this is the right way to measure the size of vertex sets. Okay. Any questions so far? Okay, continuing this recap. Great. So with all that set up, we came to study what is maybe the most important object in all the spectral graph theory, which is this quadratic form, which is a thing which maps functions or vectors or labelings of vertices to numbers. And it's denoted by this, or at least I denote it by this curly E. And it's basically the average squared distance of the function value across edges. Okay, so this notation, expectation u sim v, means pick a random, uniformly random edge. So you pick a random edge and you look at the square difference of S function's values across that edge. Okay, times factor half. Okay, and it's somehow measuring how much f is changing, like locally, along edges. And it's very instructive to compare it to the variance of f, which measures just how much f varies in this quadratic sense globally. So this is where you just pick two completely random independent vertices u and v, not from an edge, but just two independent ones, and measure the square distance between S values here. Okay, so it's always sort of good to study this quantity, but you need a scaling condition because this quantity, if you just double S values, it goes up by factor 4. So if you want to, for example, talk about maximizing this quantity, you need a natural scaling condition and scaling so that the variance is, let's say 1 is the right thing to do. So we ended the last lecture talking about the following two basic questions. Which functions f minimize this quadratic form and which functions maximize it? And the minimalization question is a bit easier, but it already starts to connect, make this connection between graph theory and combinatorics on one hand and linear algebra on the other hand, which is the real raison d'etre of spectral graph theory. So it's not hard to see that the minimum possible value of this is 0, of course. F could be just the constantly 0 function. But actually, the set of all functions f that make this have its minimum value 0 is a bit non-trivial. It's all the functions which are constant on G's connected components. And you can have a different constant value on the different connected components. You see if that happens, well, then across any edge, f will always differ by 0. And in particular, you see that if G has L connected components, then you end up getting L linearly independent functions, or vectors. As I said, functions and vectors are synonymous to us here. Linearly independent functions which make the quadratic form equal to 0. Okay? And as I mentioned last time, there are some robustifications of this fact, where if you have L linearly independent functions that almost make this quadratic form 0, then maybe you can cut your graph into L pieces that are almost disconnected. Okay, finally, on the other hand, we talked about maximizing this. And as I mentioned, it doesn't make sense to just ask about maximizing it. You have to put in some scaling condition. And you can equivalently, as I mentioned last time, either put in the condition that the 2 norm squared of the function, the average squared value, is equal to 1 or at most 1, or that the variance is equal to or at most 1. You'll get the same result in each case. And as we saw by a little arithmetic, including Cauchy-Schwarz, the maximum value of this quadratic form, assuming the scaling factor is 1, is 2. And 2 is possible if and only if the graph is bipartite. So that's another connection between this linear algebra stuff and the combinatorics of the graph. And you can see, as we saw last time, if you have a bipartite graph, if you label with, if f labels all of one part of the vertices by 1 and all the other part of the vertices by -1, then this quantity will indeed be 2, and the variance will be, the expected square will be 1. OK, that's it for the recap. Any questions? OK, so in today's lecture, we're going to get into actually even some more terminology and notation, all towards kind of getting at this idea of studying random walks in the graph G, the convergence rate, and how small sets of vertices in the graph that have few edges coming out of them can be like bottlenecks for fast convergence of the random walk to the invariant distribution, and how all this stuff connects to this quadratic form. OK, so let me remind you a couple of details about how we proved this little fact. And it started just by really expanding the definition of the quadratic form curly E. And I will omit the arithmetic, but it went like this. This curly E of f by some arithmetic equaled, this 2 norm squared of f minus this quantity, the expected value over a random edge uv of f of u times f of v. OK, and then we actually applied Cauchy-Schwarz to this quantity to say that it's at most, even the negative of it is also at most the same quantity, and that's how the bound 2 times the 2 norm squared arose as an upper bound. But actually, what I want to focus on now is this quantity. It's actually pretty similar to, as you can kind of see, it's kind of similar to this quantity. You can derive one from the other relatively easily. But we'll just take a look at it for a moment. Okay, so this boxed quantity here, star, we just write it in a slightly different way. So as we know, picking a uniformly random edge can be done in 2 steps. You can pick first a vertex according to the probability distribution pi. And then you can pick, pick v to be a uniformly random neighbor of u. OK, and then you'll look at f of u times f of v. So I didn't do too much there. But one thing I can do now is pull this f of u out here. So I get the expected value when u is drawn from pi of f of u times the expected value when v is drawn from u, well, as a random neighbor of u, of f of v. I just write this because I'm quite interested in this quantity. So we're going to think about this quantity a little bit. So, imagine u is fixed. And now what we're looking at is the average value of f on u's neighbors. Okay, so that's a nice quantity. For every vertex u, you can look at the average value of f on u's neighbors. And you can think of this itself as a function on the vertices, the function that maps u to this average. You can even sort of, in your head, imagine some kind of physical diffusion process where at each time step a vertex's label is replaced by the average, its neighbors, and somehow it's a little bit what happens in the standard random walk. So, as I said, we'll be actually kind of thinking about this function that maps u to this average. And I'm going to give a name to this function. And I'm going to give a weird name to this function, but I hope you'll come to like it soon enough. I'm going to call this function kf. So this function kf maps vertices to real numbers. Okay, so it's one of these vectors or functions as usual. And this is its definition. Kf, the function kf, applied to a vertex u is this quantity, the average value of f around u's neighbors. So why do I write it as kf? Well, you see this process of going from the original function f to this new function kf is like an operation on functions. It's like an operation that replaces one function by a different function. And it's even actually a linear operator in the linear algebra sense. Right? So we have a mapping from vectors to vectors. And it's actually a linear mapping in the sense that, if you apply it to the sum of two vectors, or the sum of two functions, you can see it's equal to the sum like kf and kg. Okay, it's just because if you replace f here by f plus g, then by linearity of expectation, you get the average of f plus the average of g. So this k, if you will, is like a linear operation that takes vectors to vectors. So it's like the classic object that gets studied in linear algebra. In fact, you can represent it by a matrix, which we will do. So let me first say its name. So it has, again, several possible names. But k is, I would say, either the Markov operator, or you might call it the transition operator for the standard random walk, or you might call it the normalized adjacency operator, as we'll see in a second, for G. And you could also call it, use the word matrix instead of operator as well. So good. So as I said, it's a linear operator that transforms functions into functions or vectors into vectors. So in classic linear algebra style, you can represent its action as a matrix. And let's think about that. And it's just a bit of a spoiler. I mean, in the most simple case, where you have a regular graph, a d-regular graph, this matrix for k is just going to be 1 over d times the adjacency matrix of the graph. But let's think a little bit about how it works. So we're looking for this matrix k, which when we multiply it against like a function or a vector, remember this thing is indexed by the vertices of v. We want to get a new vector or function, kf. Okay, and we have a formula for the youth entry of this vector kf. It's like the average of f's values when you average just over the neighbors of u. So this youth entry in the result kind of comes from the youth row here. So what do we need to put here? Basically, we need to put in each entry here, well, just a non-zero value when the associated column is a neighbor of u. And in particular, we should put 1 over the degree of u there, because when you're averaging over the neighbors of u, you take each of them with probability 1 over the degree of u. So I hope you caught all that. What I'm saying here is that the entries here, k, uv, are equal to, well, 1 over the degree of u if uv is an edge, otherwise 0. Or another way you could say this is the probability that u would step to v in the standard random walk starting at u. This is bad notation, but just saying if you're doing a standard random walk and you're at u, then this entry here is the probability that you go to v in one step. OK, so as I mentioned, in the special case where it's a d-regular graph, so all these degrees are d, then this is nothing more than 1 over d times the adjacency matrix. So in general, I mean, K is the adjacency matrix for G, just normalized so that the row sums are 1. Okay, which makes it a quote-unquote stochastic matrix. Well, maybe there's disagreement over whether a stochastic matrix is supposed to have its rows summing to 1 or a column summing to 1. But anyway, it's a non-negative matrix where all the rows sum to 1. And as I mentioned, if G is d-regular, then we have that K is just 1 over d times A. Okay. And somehow it'll be more convenient to work with K because that has a probabilistic interpretation than this matrix A, which you're more used to working with, maybe. I should also say that when it's d-regular, then K is a symmetric matrix, meaning it equals its transpose. But this does not hold true necessarily, well, at all, if it's a non-regular graph. As we'll see, though, K does have some nice property which is analogous to being a symmetric matrix. So all is well. But it'll only actually be a symmetric matrix in the regular case. OK. Any questions? Good. So let's just play around with this matrix K a little bit more. We'll see how it connects to like the random walk-in stuff. So one basic fact, which is not hard to show, is that if you have two functions, it's quite natural to look at this, the inner product of f with kg. Okay? And it's natural because it has this interpretation. It's the expected value over a random edge uv of f of u times g of v. This is a pretty natural formula over here. And in some sense, you can almost think about this as like a definition of K. I mean, K is that thing such that this is true. Do you have a question?
Yeah, so if we're saying that K is symmetric, is that only true when G is d-regular, or should that not always be true?
It need not always be true. Let's see if we can come up with a counterexample. Let's make an irregular graph. It's very hard. I guess like this graph is irregular. Okay, so if this is vertex 1, 2, 3, then the matrix A, the adjacency matrix, would be like 1 is connected to 2, and 2 is connected to 1, and 2 is connected to 3, and also to 1. Yeah, wait a minute. Am I doing this well? It's very challenging, but I think I got it. Is this right? Okay, so that's A. Okay, and so K is... this might be a bad example, though. So K will look like this: 1 half. Oh no, it's an okay example. 1 half half 1 0 0 0 0 0 0. Sorry, I don't know if you can read this. Yeah, it felt symmetric as I was writing it down, but I guess it's not symmetric, right? If you reflect this along the diagonal, it doesn't. It's not the same. This is a good example to keep in mind, though. Because, yeah, path graph, it's not so unnatural, right? But it's not regular, so you have to worry about these things, even for such small cases as path graphs. Great. So I'll just double check this formula for you with a little proof in a moment. But let me make a little observation. I mentioned this before, but this means like pick a random edge, but also bear in mind that it's ordered. Like it's sort of like picking a random directed edge from u to v, and then you look at f of u times g of v. But actually, again, the probability that you pick the edge from u to v is the same as the probability you pick the edge from v to u. So this number is actually the same if you reverse the roles of v and u, which means that, have I written this? Yeah, this is also equal to the expected value over, v comma u being a random edge of f of v, g of u, which now if you just, by commuting multiplication, move this over here, all of which is to say, this is also the same thing as kf comma g. Okay, so this is, I said that in a funny way, but this is the fact that I'm trying to get across, that these two things are also the same. And if you're an extreme linear algebra expert, then you know the name for what this means about k. It's not necessarily symmetric. If it is symmetric, and this were the usual inner product, it would be true. Yeah, self-adjoint is the terminology. An operator which has this property, like when you move it, you can move it from one side of the inner product to the other, is called self-adjoint. And I'm only dealing with like a real vector space here, so there's no funny business about conjugating complex conjugation. And this is like a little magic wand you can say sometimes to justify this. I mean, it's a true fact. And it's sort of like the replacement for the statement k is symmetric in the non-regular case. And it's like somehow this inner product is exactly cooked up to take care of everything. So yeah, this is a fact that you can use. You can move the k between the two sides. Great. So it'll share many of the same properties of symmetric matrices, as we'll see, like it has real eigenvalues and so forth. OK. Actually, let me just prove this fact. See if I can cram it all onto the same board. So why is this true? I guess, yeah, let's just try to write it. Yeah. Let me do it more clearly. So let's just expand the definition so we don't get confused here. So I'm studying the inner product of f and the function kg. So by definition of the inner product, this is the expected value of the function f at u times the function kg at u. Okay, and now we can remember the definition of kg. It's f of u. The definition of this is the average value of g around the neighbors of u. Okay, now we can do like a similar trick. We can pull this expectation to the outside and get this the expectation over first choose a random vertex u, then choose a random neighbor of u, and then compute f of u times g of v. Okay, and as we've seen a couple of times, this whole experiment together is just the same as choosing a random directed, or yeah, sure, directed edge. Okay. And why should we be interested in this particular quantity? Well, I'll just give the favorite example that we always care about, the case when f, and I guess also in this case g, are functions with range 0 and 1. So they're indicators of sets of vertices. So now imagine you have some graph G, and now you have two sets of vertices, S and T. Actually, they need not be disjoint, but I'll draw them as disjoint. And this quantity here is going to be related to like the number of edges that go between S and T. Okay, so if F is the indicator of a set S, and G is the indicator of a set T, then this quantity here, inner product of F and KG, is the expected value for a random edge UV of, well, using this formula, indicator of S applied to U times the indicator of T applied to V. Okay, this whole thing is 0 or 1. It's the indicator for the event that U is in S and V is in T. So I have an expectation of an indicator, so this is just the same. It's the probability that a random edge has the property that its first endpoint is in S and its second endpoint is in T. This is the fraction of edges that go between S and T. Okay, and this is some quantity that you may care about. In particular, if T equals S, it's the fraction of edges which are internal to S. Or a third way to put it is it's the probability that if you take a random walk in the graph of length 1, starting from the invariant distribution, that you'll go from S to T. In fact, I say that because like now I want to think about taking longer random walks in the graph. So let me make a little observation that again is related to the meaning of this matrix or operator K. So let's let rho be any probability distribution on vertices. And intuitively, you might think of it as like a probability distribution for the first vertex in a random walk. It's like our starting probability distribution. And maybe we want to see how it evolves as we take steps. And true to its name, we're going to think of this as a row vector. So instead of a column vector, we'll stack its n probabilities in a row. And as I said, this is V1 position. This is the Vn position. As I said, suppose we do this. First, draw a vertex U from this probability distribution rho. And then do one random step from U to V. Okay, so in other words, let V be a random neighbor of U. So altogether, this generates a probability distribution on V. Probability distribution of vertices you'll get if you start according to rho and then do one step. And I claim, well, we call it an exercise, but I hope you can sort of just verify it in your head as the next minute passes, that you can figure out what it is. Oh, I should have added these words. Well, if rho prime is the distribution of V, then we have this sort of formula. You get rho prime by taking this row vector rho and multiplying it against K. Because, like the vth entry of rho prime over here, like what's the probability of ending at V? It's like you consider all starting positions U, which is, I don't know, maybe here. And then it gets multiplied against the uth row here. And like kind of tells you all the probabilities you'll go to each of the subsequent vertices, given that you're at position U in row U. Okay, so k really tells you how the probability distribution transforms on vertices when you do one step of a random walk. So one corollary we have of this is that for our favorite probability distribution on vertices pi, we have pi times k equals pi. Okay, this is expressing that pi is the invariant distribution. But of course, if we start in this probability distribution row, start a random walk here, and let's say we do 2 steps, then this really corresponds to multiplying on the right by k squared, right? I mean, one step, if you start in a row and do 1 step, resulting distribution is given by multiplying on the right by k. That gives you rho prime. If you multiply on the right by k again, you'll get the distribution of vertices after 2 steps. And that's the same as multiplying on the original distribution on the right by k squared. Okay, so it seemed kind of believable. Let me say some more in symbols. Because I guess I sort of only explained to you how k squared acts on probability vectors. But in general, k squared, which is the same as k composed with k, if you think of k as an operation, how does it operate? It operates as k squared applied to a function f and then evaluated at a vertex u. It's the average of f's values around like the sort of 2 neighbors of u, meaning the w's that you get after doing a 2-step random walk from u. And again, hopefully it seems believable, but just to get used to all of this notation, I'll do a proof. Okay, so given f, just so we don't have too many symbols, let's let g denote kf. And so, therefore, k squared f is like k applied to kf, which is kg. Okay, so k squared f at u is kg applied to u. And now let's remember the definition of the operator k. It just averages g's values over the neighbors of u. So this is the average over v, a neighbor of u, of g of v, by definition of k. But now, what is g? It's kf. So, okay. So this is the expectation over v, a neighbor of u, of kf applied to u. Okay, to be continued on the next pane. Okay, and then we'll remember inside the expectation the definition of k again. Sorry. So it's the expectation over, is this looking good? This should say v. Good. So this is the expectation over w, a neighbor of v, of f of w. Okay, and now we're basically done. So we put these expectations together. We're first choosing a random neighbor v of u, and then we're choosing a random neighbor w of v, and we're looking at the average of f's values on w. Okay, so I hope you'll therefore agree that, in fact, for all natural numbers, t, how does k to the t operate? K to the t applied to f evaluated at u is the expected value of f's value on some w, where w is formed from u by taking a t-step walk. Okay, so KT's operation has this property. I mean, the way to think about it is like for t times, you like replace each vertex by the average of its neighbors. You do this a bunch of times, sort of the f values like diffuse throughout the graph. And this even holds for t equals 0, right? Okay, here I'm raising a matrix to the 0th power, so I get the identity matrix. I of f at u is just f of u. And indeed, this is the average of s values over all 0-step random walks starting at u. Okay, so this k will really be the thing we'll need to study when we're thinking about like how fast does a random walk in this graph mix? How long does it take for a random walk to get close to the invariant distribution? And it'll indeed tell us about sparse cuts in the graph.